sticking up. Today we're gonna talk a little bit more about networks, and then more hypothesis testing with mental tests and PCA, a way to summarize several social behavior that you might have. And this afternoon we're gonna start adding time to the mix. So talking about temporal models. So now in the morning, mainly two things. How to calculate local network metrics. So all the metrics you're going to see this morning are related to the node, to the individual and also social network. And then I'll explain you briefly how we can use randomization techniques to estimate confidence intervals for these metrics. Or if you're working with something else in your life, you can use the same idea later. We know what a social network is by now. Individuals connected by some sort of links, relationships. In our case, would usually be the association index, or it could be a rate of interactions if you're working with a different social system. We've seen yesterday metrics for the whole network, the global properties or the topology of the network. Today we're going to look into the nodes. So some of them, there's more than this. Very basic one is they're all related to centrality. So the first one is the degree or strength of the node. It's basically this guy over here would be the number of links they have, or the sum of all the strength or the weight, or all of the weights of their links. The other one is closeness. It's a measure of how central this individual are in the network, how close it is to all the nodes in the network. Then betweenness, review, it's based on the concept of the shortest path length, and it's so it measures how connected this individual are to different subsets of your network. We have also cluster coefficient, same idea that for the whole network, but then we look into the individuals. So we start getting a sense of if an individual are more central to the network or more peripheral to the system. Right. So degree and strength centrality is very, very simple. Degree is, both of them will give us an idea of influence of each individual over the rest of the network. So the degree is simply just the number of nodes an individual has. Here, for example, this is a weighted network. This is the strength of the link, 1, 2, 3, 4. So the degree of this guy would be just 2, because the number of connections they have, the number of associates it has.
Does it matter the strength?
No, degree is the binary centrality, so just the number of them. So the number of links of a given node. And in a social network would be the number of individuals, associates, or friends, or buddies. And the strength, it takes into account the weight of these links. So it would be just the sum of the weight. So the degree of this guy would be 2, but the strength would be 6. Good? Simple enough, right? So here another example. The degree of this guy is 0, has no connections. Sorry for him. And this guy, on the other hand, is part of the giant component of the network, and he has a degree of 4. 1, 2, 3, 4. If you're dealing with asymmetric matrices or direct networks, which is usually the case for interactions, you can have in and out degree. So in degree is the number of nodes that you receive, and out that goes out of the node. So we just have, it might be the same or it might not. So this guy receives 2, but he gives just 1. This is a very simple concept. There's a way to, recently in 2010, these guys here, they proposed a tuning parameter for the weighted versions of all these centrality measures we're going to see, which they call alpha. So all of the basic centrality metrics, they're based on the number of links, right? When we start incorporating the weight of links, kind of lost just by summing them, we kind of lost the idea of number of links they have. For example, you can have this guy with just 1 link, but then the strength is super high because this connection is super strong, as opposed to this guy who has more connections, but then they are weaker. So the tuning parameter gives you the opportunity to give more emphasis on the number or on the strength. So by varying this alpha, you can have a combination of degree and strength at the same time. For example, the node A over here, the degree would be 2, right? 1, 2 connections. The traditional strength would be 8, 4 plus 4. And then when we add this alpha, we can give, if it's 0, it will be just the number of connections, and then if it's 1, would be the sum. But you can have more than that. If you think that the strength of the interaction is more important, you can give more emphasis to this. So the new strength of this individual could be up to 16 or more if you increase alpha. Or values between 0 and 1 would give you something in the middle. So it's just a way to, depending on your question, you might want to give more emphasis to the strength or to the number or something in between. So it just gives you that opportunity. The way the alpha works is just the product of the number of nodes and the mean weight of their interactions. So if you have an alpha value that is between 0 and 1, having more connections is more important in your case. If you have alpha greater than 1, you're giving more importance to the strength, to how strong these connections are. Any question? It's just it's a recent improvement on the metric. And this alpha value you can apply to other centrality measures like closeness and betweenness, the ones we're going to see next. So closeness centrality. So we see degree centrality, number of connections and strength of these connections. Now the closeness centrality, well, technically is the inverse sum of all shortest paths from a given node to all others in the network. It's a way of measuring how connected a given individual are to the entire network. Sure. In other words, you're trying to see who in this network is the shortcut to everybody else, who's the more connected. So remember, shortest path is the shortest path. It's the number of steps, of links that you have to take from one individual to the other. The shortest one. The smallest number of steps you take from one individual to the other. So for each individual, you're going to calculate the distance to all of the others in the network, and this is going to be the inverse number of all shortest path, if that makes any sense. I'm going to try again. To make any sense, it's a relative measure of a given individual to everybody else in the network. It's an idea of, we're trying to see how central this individual is, how much of a shortcut this guy is in terms of paths. So the idea is the central individuals, they tend to be closer to the others, so there will always be a short path passing through him as opposed to the other peripheral individuals. So to reach this guy, you always need to add You need longer paths as opposed to this or this or this guy. So this is a good measure if you're trying to infer the influence of an individual in the network flow. Say, for example, information. If in a social media, for example, if you make this guy, if you give one idea to this guy, it's more likely that you'll be able to spread this information to other individuals, or in terms of disease or whatever quantities is flowing in the network. Another measure of centrality is what we call betweenness. So a word with many E's, many N's, many S's. Never seen that. Love it. So it's the number of shortest paths, again, that pass through a given node. Usually, a node with high betweenness, it would be in between two groups. So the way we calculate is super simple. It's the number of shortest paths that pass from a given node J to K. Say this is J, this is K, passing through the node of interest, node I, divided by the total shortest path that pass from these guys to these guys. So when you have individuals with high betweenness, it tends to connect modules. It tends to be in the middle model. So if you have, I don't know, your friends from school and your friends from around your house, and this guy makes the connection between them. So it's a more, in this sense, he's more central to the network. And it's important that he may control or funnel the network flow of disease, of information. If there's a great idea happening in their school, the guys that don't go to school but live close to him might be able to get that idea through this guy. Good? Any questions? So we've seen three types of centrality metric. They're all related to the individual now. So degree and strength, closeness, and betweenness. Here's a recent example. I put this paper on the library. It's a really cool example, actually. They're working with crows in New Caledonia, the ones they still use. And so this guy, for example, I bet he has a pretty high betweenness. So with the technique of using tool to get food, it's about to spread in his network. This guy might have a high influence on it. If you want to take a look, here's the paper in the library. Okay, just to illustrate how betweenness work, let's calculate for this toy network over here. So it's, just remember, geodesic path is the same as the shortest path. So it's the number of them that pass through a node. So the betweenness of D, let's count how many shortest paths passes through this guy. So many THs, dude. You make my life hard. So here you have two shortest paths from A to E, and one of them passes through D. Okay? So half. 1 out of 2. Another one, if you want to go from B to E, we have again 2 ways of getting there, and just one pass through D. So,
yeah, sure. Yeah.
okay?
Yeah.
So there's one shortest path, another one.
Yeah.
So it's half plus half. The betweenness of this guy will be 1. Now the betweenness of E will be 0. So you go from here to, you don't have any shortest path passing through E. Betweenness of B, for example, you have from A to C, you may pass through there, so we have 1. A to D, we also pass through D, and all the way to E, you're gonna pass through B. No matter how we go to E, you have to pass through D. So this guy has a high betweenness in this situation, this betweenness of 3. Good. Seeing the clustering coefficient yesterday, and the local version of it is the same, but for each individual. Instead of a single metric for the entire network, how clustered, how connected your network are, how many of these triangles we have in the network, try it. It's the same idea, but we break it down for each individual. So I'm going to see if these guys are member of cohesive groups. Yeah. So we're given, for a given node, is the fraction of links by the total of possible links with their neighbor nodes. So I'm showing here. We are essentially asking if the friends of our friend, their friends, so this guy, it's two friends, it's these guys, this guy, if they are also friends, if they are also connected. So we have those two. And just refresh your mind, there's a different way we can do that for weighted networks. You can use the totals, the mean of the weight of their links, or the geometric mean, or just taking the maximum or the mean. Here's easy to say. So, for example, we can average this total sum of their link weights, or use the geometric mean, or just take the maximum one or the mean one. So, again, depends on, you can play with that, depends the type of emphasis you want to give. To illustrate, so the clustering coefficient for A here. A is connected 1, 2, 3, 4 individuals, but these guys have potential 6 connections between them. So between these two, we have 1. Between these two, we would have another 1. Between these two, we have another 1. So, but out of them, just 1 is connected. And also, you could connect this guy with this guy, this guy with this guy. So we have 6 potential. Among the individuals that are connected to A, we have 6 potential connections between them, but we see just 1. Is that clear? No? For example, it has 4 connections, right? So this guy could be connected to this could be connected to this could be connected to this could be connected to this, and so on. But out of all of these possibilities, we have just 1 here. So it's 1 out of all the potential connections we have. So the clustering coefficient of this guy is 1 by 6, 16%. Then we do this for all individuals, and then you have a measure of how cliquish, how these guys connect, how their friends are also connected. So let me see for B. For B, yeah, you have 2 connections, 1, 2, but then the number of potential connections they could have is just 1, just this guy connected to this guy, and they are connected. So that's why this clustering coefficient is 1. Don't look very happy. It's higher because it has less connections, and all of these connections are connected. This guy has many connections, but their connections are not connected.
But before it was 1 out of 6.
Yes. So this guy has 4. 1, 2,
Yeah.
4, right? And you can have 1, 2, 3, 4. Let's see.
The one down to C.
Sorry, C.
2.
Yeah.
Yeah.
This guy and this guy. 6. So
Yeah,
out of these 6, we have just 1.
1.
So it's 1 divided by 6.
And now there's that 2 possible connection. The next one.
The B.
For B.
Yeah, so this guy has 2. And this 2 has 2 individuals, and the potential connections between them is just as 1.
So is it 1?
And
So it's up.
And he has, so it's 1 divided by 1. 1. So the clustering coefficient of these guys is higher than these.
Yeah.
It's the proportion, right? So it's one way of measuring. So if you're not, it depends on the emphasis you want to give to your centrality measure. One centrality measure is just the number of connections. So if that's what you want to measure here, A has a degree of, the degree of A is 4. The degree of B is just 2. But the clustering coefficient of A is 16, and the clustering coefficient of B is 1. So it depends on depends on the question.
What kind of like biological significance is like would this number give you?
So it's an idea of how cliquish this individual are, how connected his friends are with his friends. So it's the friends of her friends are also friends. In this case, that's true, and in this case, not so much. So he's more central of the network in terms of number of connections, but among his little ego network, the ones they are connecting, he is more connected. So it depends on this scale you are looking at. So let me see.
So would you, I mean, like thinking like disease, would you keep like the vaccine to A or to B now?
I think to A or to B.
Yeah.
I think to A in this case.
Okay, but then what's the point of calculating the clustering coefficient?
Well, maybe not for this question. I think.
This question.
Yeah, you want to see how locally famous this guy is, maybe how their friends are connected. Any other comments for network people?
They can be very arbitrary. Like you really have to think carefully about what you want to do with a network measure. Yeah, so it's really...
Yeah, just can you picture a scenario where I would use this over like the other coefficient? Yeah.
Any thoughts?
It's, I'm probably never going to use it anyway, so it's okay.
Any?
Yeah, I guess it really, like for me, it's something that's very useful because I need to know which individual are like keystone in mind, like which I want to make contribute the most to the social organization. For example, I have a group that is very established and they interact, they live in permanent group, for example. So the degree of clustering coefficient makes sense, especially like in the social weaver. So they live all together in this giant nest, and then within the giant, that's one social unit. And within a giant nest, you have like many subunits, which are mainly composed of breeding group. And clustering coefficient, like you can see whether the social association you see reflect the breeding group, for example, composition.
Okay.
You know,
Yeah.
and you can use all this. So for my system, actually, this kind of centrality matrix is what I use most than modularity or things.
Thanks.
Thank you.
Yeah, I mean, a matriarchal system would also be good examples of where centrality measures if you're looking at mating interactions, gene flow, that kind of, lots of possibilities.
In one of my chapters, I'm hoping to publish, I'm testing whether cooperation may evolve through like social prestige, for example. And if it has evolved through social prestige, meaning you cooperate because it increases your energy and you get more reciprocation, I assume that individuals that cooperate the most will have the most high degree, for example. Because that's a good measure of social prestige. And then so that's how I use social network analysis to test my hypothesis. I guess it really depends on the system and the question you want to ask.
Yeah, degree would be a good measure for social prestige because if you have 17 connections, maybe you're more popular than one that's just you, for example. Yeah. We can also use that tuning parameter here for clustering coefficient. The idea is choosing how much emphasis you want to give to the number or the strength of the interactions. So if you're dealing with a weighted network, not an array one, you could traditionally you can just use the binary version of it, number of links, or the weighted version of it is sum of the strength of the links. But with the tuning parameter, you might want to combine both and give more emphasis to the number or the strength. I'll give you an example. For example, the path from A to B is just one in terms of number and strength. So we have the binary distance is 1, the weighted distance is 1 because it's 1, and if in this case the timing parameter won't do much, any variation. But from A to B passing through C, we can have 2 links, or we can have just 1. You see what I mean? You can have this connection or this stronger connection here, and depending on the alpha value, you can combine these two information. If you have a alpha that is smaller than 1, so short path with weak links is favored over long paths with stronger links. So we can go from A to B here through a weak interaction or to a longer interaction but stronger one. Depends on what the strength of interaction means to you. If it's the association index, for example, yes, you have a way to go from here to here, but this might be super rare, as opposed to these guys is longer, but it happens more often. So it depends on what your link weight means. Well, you can play with that as well. If you have alpha values that is greater than 1, then we are giving emphasis to longer but stronger paths. So again, it depends on the question you're using. If you work with clustering coefficient, you might want to think about biologically if that makes more sense for you. Alright. So here's some other metrics that we have available. There's quite a lot of them for centrality measures. They are all more or less based on number of interactions and short paths passing through this node. So reach is another one. All of these are available in SockRock. We can calculate them now. So it's an indirect metric of connectors. It's the number of nodes, I think this should be or 2 or fewer steps away. Fix that. You can have eigenvalues centrality, so it's how connected an individual is within the network. So it could be either because it has a high number of connections or strength, or because it is connected to individuals with high degree or strength. So either you're popular or your best friend with a popular guy, which is a strategy that works well in high school. If you're not that guy, you can at least be friends with him. And affinity is the average degree of its neighbors. So we're not looking, you have a focal node, but you're going to focus on the degree of their nodes connected to it. So we want to see if these guys connected to others with high degree. It's a similar match. They're all kind of related.
So for affinity, you'll be looking at how connected this focal node is. Wait, just a second. So you'll be determining the connectedness of the central node by the connectedness of its connections.
That's right.
Okay.
So it's one way of interpreting more biologically what these guys mean. So degree is actually how many friends or connections someone has. The reach would be how central this guy is to the network. Clustering coefficient, how cliquish they are. And betweenness would be how important they are to the flow of things on the network, of quantities, to the integrity of the network. Because if you can remove a guy with high betweenness, you might split the network. And the weighted versions of them would be pretty much the same, but if you have more information, I'll have also the weight of the links. So how many friends or how friendly they are, here would be pretty much the same. And affinity, which is the weighted average strength of your neighbors, what I just said. So how important your friends are. If you're connected to a popular group, if you're friends with someone who has a rock band and attracts sharks with that, maybe you're a great guy as well. That's you. Good.
Or someone with a boat to go see orcas.
Yeah. They might attract orcas, I don't know. Maybe we should try that project. So here's an example with sperm whales. This is a group of 7. It's a group of a social unit of sperm whales that is very often seen off Dominica in the Caribbean. They have been tracking these guys for more than 10 years now, so they know a lot about them. So here we have calves and adults and juvenile. So we can calculate all of these metrics for strength, reach, and clustering coefficient. Oh, it's raining. It's gonna mess up my hair. So we have strength would be just the sum of 2 connections.
You get an afro.
I forgot my hair dryer at the beginning. Yeah, you can be friends now. So yeah, we can calculate for all of these metrics for each individual, and you can see they might be correlated. So a guy with high strength, the calf here, and also might have a high reach in the network. So he's highly connected to the network. This guy here, he has lots of connections and stronger ones, but he's not. His clustering coefficient is low. Actually, it's the lowest one. So here we have negative correlation between clustering coefficient and centrality and other measures of centrality. So the better associated this guy is, the calf, less clickish he has. It means that he has lots of connections, but their connections are not connected as well. See, we have time. Sweet. Okay, so we have some measures, some metrics for each individual, which is great. And yesterday we also measured some other network metrics. But usually when you have an estimate of something and we don't have confidence around this value, it's usually not very useful. So we usually want to add at least the standard errors or confidence interval to see how confident we are with that specific value. So traditionally, we have data, and then we estimate something, and then we can create the confidence intervals around this estimator, around this metric or statistic or network property. We can use that from the data or itself, or using a biological model, and then we use a statistical model, and then we get estimation. But sometimes we don't have neither a clear biological model or a statistical model to estimate here. So what we do then, if we don't have a good model, we can use, for example, in a traditional case, let me give you an example not related to social analysis. But we are just looking at the sex ratio of a population of voles. So we go there and we go to the field, trap them and collect. We'll have 12 males and 50 females. So the ratio would be that, 12 males divided by the total individuals. So we have 44% of this population males. And then we can estimate the standard deviation just assuming that a binomial distribution. If we assume that, then we can calculate using these ways. So it would be, I think, let me see, 44 would be, well, there's no point for me writing that, it's already there. Anyway. I forgot what you should. I think this is the day. I think in day one, we talked here. So when we're talking in the day one of the precision of association index, we can, if you assume they are the binomial distribution, we can just calculate the standard error of a given metric here, alpha, using this formula. 1 minus alpha divided by the total, and the square root of this. So this is one big assumption. We don't know if our distribution will follow a binomial distribution or not. So we don't have this clear biological model to base. So if you can assume this, if you have this model, this clear we can use a theoretical distribution like a binomial one to estimate our standard deviation. So in this case, we have the observed ratio and an estimate of confidence around it. But what we don't have, and that's going to be the case for all network metrics, for example. We don't have a clear, we either don't have a clear biological model, or trying to use a statistical model is too difficult, impossible, or even boring. Or it's too complicated to be useful, or even the model might not be either valid or accurate. So we might need way too many, a large number of samples to be able to estimate using a theoretical distribution. So when we don't have, and this is often the case for networks in animal social analysis, we can use two resampling techniques. One is the Jackknife, and the other is the Non-parametric Bootstrap. Try to explain how the Jackknife works in a few minutes. So here's our data. Go there and collect a bunch of samples. In that case, would be the weight of an individual. So we collect a bunch of samples, and we use a statistic, say mean or what is that face? I don't know what you're talking about. Any statistic, could be the mean, or it could be, I don't know, whatever you want. The median. Let's call the mean. So we collect a bunch of, I don't know, weight of some individuals, and you have the mean value of it. Now we want the standard error around this mean value. One way of doing it, we replicate our data, missing one unit. So we're gonna take the entire data set and skip, and notice that we skip the measured one. So x1 is not here anymore. Now we have the x2 to the end, and then we calculate the same statistics and say the mean, but missing the unit 1. Okay? Then we do that again, missing the unit 2. Notice we have 1, 3. Then we calculate mean of all of our data without the sample 2. Is that clear? Mm-hmm. And we do that for all of them. Now we convert our statistics into pseudo values. So now we have the pseudo value here, which is the number of observations plus the statistic minus the jackknifed one, which is all of them minus 1 plus the statistic missing the first one. Is that, are you still with me? Okay.
So it's n minus 1 times
Sorry?
Just n minus 1 times the mean of the first jackknife.
Yes, yes. And then you do the same for the second jackknife. And the same for if you have 1,000, you do this 1,000 times. So we start with your data in one value of your statistics, say the mean, and then you have 1,000 pseudo values based on you missing your missing your samples. So you do that 1,000 times. Now we have the jackknife estimated of S. S is our statistic mean, based on the pseudo values, not of the values anymore, but the values that we were missing. The replicate's missing one sample. Are you with me? More or less. Yeah, everybody's like, what the?
So basically, the pseudo value is the difference between the original mean, basically,
Yes.
minus the new one calculated
Yes.
with a missing value. So it's a,
Yes.
let's say the starting first one is the distance between the original mean, basically, value multiplied by and this one calculated minus the first element. And then it carries on, so that basically it's still the mean of everything is still the original mean that you calculated, but you have something around that you can
Yes.
calculate your standard error or your confidence interval.
Let's say we have, this is our original weight of individuals. You have 10, 20. Then we calculate the mean here, which is 40 divided by 4, 10, right? So the mean would be 10, and this is our sample. So the jackknife replicate would be, now the first one would be the mean of this. So it would be 30, it would still be 10. No, this is, no, this is not 40.
It's 50.
50.
50 divided by
Where for? Good. So then we toss this one out and then calculate the mean again. Then put it back and toss this one out and calculate the mean again. And then the pseudo values would be the mean plus the number of samples we have minus the mean of these replicate here times the number of the values over here. Then we have a different one. Then we have this distribution of 1,000 jackknife replications. And then we calculate the mean of our pseudo values here. And we have now this jackknife distribution, then we can calculate the mean, and from this distribution we calculate the standard errors. So this is your jackknife standard errors for your observed mean.
It's like cheating.
Like cheating, yes.
Cheating.
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 So you make up the data you.
Exactly. So yeah, it's
This.
similar to the new model things. If you don't have a good reason to use a theoretical distribution, you create your own. You cheat. It's tough for us, but oh man.
Normal inference is also cheating.
Yeah. But this is blindly cheating.
Yeah.
So you try to hide it. So you put it there.
So we remove biases, but it's rough and ready. It's like a very, cheating way. So it's usually conservative because it overestimates the standard error. So you're gonna have, say your mean is 10, you're gonna have a large standard errors. So you have a large, you can miss a lot. 10 is a rough estimate. Well, if your data is not independent, you can use blocks of units instead of your whole distribution. So if you have autocorrelation in your, not in the case of weights, but if you have all of your samples and they're autocorrelated, you can do estimates into blocks of your distribution. Just remove that. And one thing is assumes normality to calculate the confidence intervals. Okay. So let me give you an example with gill weight and body weight in crabs. So this is the correlation of this with this, gill with body weight, and we got this value. We want to add a standard error to this, so a measure of precision. So how can we calculate that? So first, you calculate using that technique of missing one value out. So we take this one, calculate the correlation between them, and then take this one and calculate the correlations and so on. Then the mean correlation of this jackknife distribution would be around similar to that one, but it's a different value, you see. And then from this distribution, we can calculate the standard error using that formula. The standard error of these pseudo values will give us a little bit of confidence. So we could do that with network metrics if you want. If you have the degree or clustering coefficient, we could do that as well.
And then you use the real value plus the standard, plus minus the standard deviation, not the pseudo mean value.
Yeah, use the real value. Yeah, you don't care much about it. So you would present here. 0.68. That would be your correlation. So just okay, Jackknife is one way of doing. The other way is Bootstrap. There's two ways of doing Bootstrap: parametric and non-parametric. You're going to look into the non-parametric Bootstrap, which is what we usually call, when you see Bootstrap out there, they're actually most of the time talking about non-parametric Bootstrap. So it's similar idea, but now resampling with replacement that you asked yesterday. So the Jackknife, we miss one out every time. With the Bootstrap, it is the same, but then we're going to put all of these values in the back and take the same, say if you have 10 values, you take 10 values, but with replacement. Show me. So the Bootstrap replicate here. So we have 1, 2, 3, say 10. Our first one, we might get, it's not this way of doing. Just put the same numbers. So let's see, we have a bag here. And we have x1, x2, x3, x4. So those are our samples of whatever it is, say the weight of an individual. Then you come here and you calculate the statistic as, let's say it's our mean, which is 10. Now we put all this value in the back again and take 10 values of 10, but with replacement. So we'll go there and take x2, put x2 again. Take x4, put again. Then I take, say, x2 again, and then x3. So I have a different sample now. Good? And then I'll calculate the mean for this. So the mean here, say, is 12. Then I start over and do this over and over again at least 1,000 times. So it's a resampling technique, but with replacement. So we allowed that, I don't know, you could even have one sample that is just x1, 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 for example. We have all possibilities. Good?
But the probability of that one is much lower.
It's lower, yes. So the more, if you do, I don't know, a billion interactions, you might even get that. The more you do, the more precise it will be. And then we proceed. So we randomly select new samples with replacement, and then we can calculate standard deviation and confidence intervals from this distribution of our statistic as mean in our case. So usually from 100 to 10,000 replicates will give you a good estimate. Show you an example, and then if you have any questions. So you again mean gill weights in crabs. So say this is our observed data. We have 11 individuals. And then we calculate the median of this distribution is 195 milligrams. Now we can do some bootstrap replicates. So this is our observed one. Then we sample it, and we got this different one. See that all the values are there. So this guy is here, this guy is here, this is here. Here it is again, so twice. Here is again. So we can have some replicates. So we do that and we calculate the median again. Now we have one replication here is this. Then you do it again. You got this value. Do it again and again and again. So you have a distribution of medians. And with distribution of medians, now we can calculate the standard deviation if you want, or the confidence interval if you want. So at the end, we will have so this is the observed statistic. Then the mean out of 1,000 samples, we have, say, a confidence interval of this. So he would present the median is 5, and writing exactly what's there. So that's not very, but anyway, so you have your estimate and you have confidence intervals or standard error around your estimate. So this is our observed value, and this is how much it might vary around. Good. So we can use that for that. All of this to say that we can use that for network mappings if you want, or even association indices, or U weights and crabs. Why not? So let's just compare this guy. So Bootstrap is usually a better estimate of confidence. Remember that you calculate the confidence intervals with Jackknives, you have to assume normality, which is often not the case in network data, for example. So that will be a better one. Usually underestimates precision, so it's a very conservative measure. What else? Reduce biases. Anyway, both of them are useful when I think about which one is the best for your case.
What did you mean when you said okay, so
Self-comparison here.
it's independence among the measures, is that what you mean by?
Yes, remember we are doing web replacement. So that would be a problem. Which is not a problem here because you're always taking one out and using the others. And there one you can have, remember the 320 will appear like several times. And let's see. So both of them will give us estimates and bias of a given metric when you don't know that it's the real distribution, or this distribution is too approximate or is impossible to relate to it. So I showed you the non-parametric bootstrap. The parametric bootstrap is very useful if you know the model, but it needs a lot of programming. That's why I skipped. And the non-parametric bootstrap has less assumptions and it's usually very applicable. The Jackknife gives you approximate estimate, and better to use the standard error because the confidence intervals assumes normality, and it's useful if the bootstrap is not applicable, then go for Jackknife. So I think bootstrap is your way to go.
What, Sorry, can you repeat why
Yes.
it needs independence?
Let me see. Needs independence because you're resampling with
Replacement.
replacement. Yeah.
Okay, think about it.
I'll think about that as well.
If the values are not dependent on one another, replacing, some values will influence the others because now one value is dependent, or like several values are dependent on other values, and so it influences how the values, like, I don't know, are weighted, I suppose, or how important they are in the situation. So you may get a median or a mean or whatever that's completely wrong because now all of the values that are dependent on one another have now been either removed or duplicated. Does that make sense? That's how I understand it. Is that correct?
It makes sense to me. Yeah.
Okay.
We have half an hour. We can now run these things in Sockprog R and Gaffi GP. So, do we have Gaffi and Sockprog and R working properly, or should I just show, or should we do it together? More or less. Some of them are working. So, just show you quickly how you do in Sockprog. It's super simple after you read through all of the basic steps. Basically, just click in network analysis statistics and we'll calculate for you either for the whole network or for each individual four different metrics, and you can choose if you want bootstraps. So we just all this time that's spent here, you just click here and it'll do for you. And or you can use the results of your if you run the permutation test first, you could also use those random matrices to create standard errors for your network metrics. So essentially, you're running a new model here for networks. You can have the output for each individual or not. You can have it exported in a text file or not. And you're gonna see the output would be something like this. So you have your individuals here, and Sockprog calculates 5 metrics: strength, eigenvector, centrality, reach, cluster coefficient, and affinity. So we give you for each individual. If you have a class, males, females, adults, males, females, or juveniles and adults, you can add this class here. It will also calculate for these blocks, these categorical ones. So we have the mean values for all of these metrics for each class, say for all females or all males in this case. And you have also within and between classes, so you have females to females, females to males, males to females, and males to males. So have all possible combination. The overall mean, and it also gives you the correlation between some of these metrics, as I showed you with these primwells. So you can have the strength correlated to the cluster coefficient, or the strength and the affinity. So what does that mean actually? So strength will show you how well connected individuals are. So we can rank them is a measure of centrality. This is also a measure of centrality, but specifically how central to the networks these individuals are. Higher values, more central. This is the indirect connectedness. This is how well connected the neighbors are to each other. And here, how well connected are the neighbors. And again, how do well-connected individuals connect to the one another? That's what you're trying to ask with this combination here. So to run in SockRog is you click 3 times, 3 buttons, and you get all of this information. Oh, and you might have bootstrap standard errors for your metrics if you want. And now you know how to calculate them.
And what if you, instead of running Bootstrap, you run the new model permutations?
You also give you this. I think the way you will calculate is this matrix for all of the random matrices, and then you have distribution, and from that null distribution you calculate the standard error.
Okay, so you still give you that also.
Yes. So it's with the permutations, what you're doing is exactly what we done yesterday with the null models. So it's a different way, different randomization procedure.
I was just wondering how many bootstrap resamplings SockRog does. So I wasn't sure if it was that.
Does it give you the option, right?
Yeah, top right box was still used, or
I don't know how many. I can look it up for you, but it would be
I just wondered if you knew.
at least 100. That's for sure.
Yeah,
Or
1,000.
probably 1,000.
And it doesn't give you the chance of the Jackknife in case you want to.
For this one, it doesn't, because it just assumes that the bootstrap would be, I don't know, better in this case. And we're gonna use Jackknife and SockRog for other metrics, like this afternoon with the lagged association rates. So temporal models, then you use Jackknife for that. So,
Not in
not yet. Exactly. I'll show you quickly in Get5 how to do it. It's super easy. In that corner, you have this window in the corner, and it gives you some metrics here. Just click run, and if you go. Yes. Yes. Let me see, let me try.
I get all the data behind it, so
Okay.
but it just doesn't visualize it.
So what do you guys up to for us to do it together, or just show in the slides? What do you guys want? I'll see if I can show Get5.
Yeah.
Is that well for me?
Which version
8.2?
do you? Oh, yeah, 1.7. So maybe
Yours is newer than mine.
it's no 0.7.
Oh, 0.7.
Yours is newer.
Did you just try the old trick, closing everything and starting again?
You try switching
So here in Get5, you just in the corner here you have all of the, not all, but some metrics. So average degree will count the number of connections each node has and plots you this distribution, and your average degree is over here. That's very simple. If you want to account for the weight of the lanes, he also does the same. It's the same as well. Maybe it's a better one. What else do we have? Eigenvectors, centrality. Choose the number of interactions. And it will give you is 0,0,0,1. This last thing here, I don't know if you guys know, it just means and it's 4. So it's actually this value plus, it's 1 plus 7. So it's a pretty tiny value. This is what this means. Yeah. So you can, or average clustering coefficient, blah, blah. You keep it there. So in Getify it's simpler, but you don't have any measure of precision. Now, if you want to do step by step, we can do all of this in R as well. So in R we have 2 scripts here, one for local metrics and the other for Jackknife and Bootstrap. So local metrics. For this one we just need a tnet package. If everybody has that, you could, so we can do it together. You guys up to do that? Sweet, let's do it. Very simple. Enter the fake elephants. Calculate the association matrix. Make it as an agile list. And there we go. So we have functions to calculate the weighted shortest path length, and then the local clustering coefficient, and then some of those metrics: betweenness, closeness, centrality, and degrees centrality. And in this package, it gives you the opportunity to use the alpha tuning parameters. So if you wanna give more emphasis to how strong the connections are, you increase alpha. If you want to go binary, you go all the way to 0, and anything between 0 and 1 will give you like a balance between this. Towards 1, it gives you emphasis to stronger, other than number of connections, and then you can calculate all of this.
Shock proc doesn't give you the chance to use alpha.
No. Yeah. Alpha is a pretty new concept. Yeah, since 2010. And I think only in this package, tnet, there's this guy